So today what we're going to be talking about is distance traveled. And you're not going to see the connection to antiderivatives yet, but it's coming, okay? So trust me on this. This has something to do with the antiderivatives that we're going to be looking at throughout this unit, okay? So here's a first problem, okay? Car travels at a velocity, v of t is equal to 60 miles per hour. What is the total distance traveled by the car in 2 hours? So we're going to just do this a couple ways. We're going to look at it graphically, and then we're also going to look at it. Okay, what does this mean to go 60 miles per hour in 2 hours? Okay, so you can from physics, if you've had physics, all right, is distance is equal to rate times time, and we're going to use this up front to figure it out. So what this is telling me is that if we the distance, if we know the rate, which we do, 60 miles per hour, right? 60 miles per hour, and we multiply by that by the time, which is 2 hours, right? Our hours are going to cancel and we'd be left with 120 miles. Now, how does that show itself in a graph when we're looking at the velocity? So the velocity is constant, right? 60 miles per hour. So that's why you're seeing at the 60 that there's a horizontal line right here, because it's always staying 60. And I want to know how far did it travel in the first 2 hours. Okay, so we're going to use the graph to figure that out. Okay, so I'm going to do some shading, and I'm going to shade between 0 and 2 and up to the graph of 60. Okay, so I'm going to pause right now and I'm going to shade it in. So I've shaded in the region for the first 2 hours and the 60 miles per hour. And I want to show you how we can use this shaded region to figure out the same problem. Okay, so if you take a look at this, all right, this has a length of 2 hours, and the units are hours. So this would be 2 hours. And this right here has a length of 60 miles per hour. And if we calculate the area, it would give us this, right? So we can get the distance by taking the length times the width, or the base times the height. Okay, so in this case, the distance would equal, and we could, again, the length or base or height is, the height would be 60 miles per hour. The order doesn't matter how you multiply these, okay? But it'd be 60 miles per hour times, and then this 2 hours. So we're getting it another way, right? And so distance would be 120 miles. So this is easy. We wouldn't really need to do this, all right? We wouldn't need to find the area, okay? If it's a problem like this where it's a constant velocity, okay? But when that velocity is changing, how can you figure it out? Can we still use this area to figure it out? And you can, okay? And that's where we're going with the next problem. So what I want you to understand is, instead of doing it this way, we can find the distance traveled by just finding the shaded region and then calculating the area of that shaded region, okay? So once again, I know a car travels at a velocity, and because this is a formula, the velocity is changing over time, and it's still in miles per hour. What is the total distance traveled by the car in 3 hours? So what we're going to do is we're going to shade the region from 0 to 3, because that's going to represent my 3 hours. And then this is going to be the velocity that is changing. I'm going to show you we can calculate this, okay? So let me go ahead and shade. Okay, so I've shaded the region, and now what I'm going to do is, this is kind of a strange shape, but there's a couple ways you could do it. All right, one way to do it is to break it up into a triangle and a rectangle. And what I'm going to do is I'm going to draw it this way, and I'm going to connect this right here. Okay, so I'm going to do this 2 ways. Another way is to look at this as, this is a trapezoid, but you'd have to know the area formula for a trapezoid, right? I am going to go over that, okay? But right now we can just look at it as a triangle and a rectangle. So method 1 is going to be a triangle and rectangle. Okay, so I know that this triangle, all right, would be, the area of it would be 1/2 the base. So we know this base is 3 hours. And we're going to multiply that by the height of the triangle, which would be this distance right here. So this is 10, each of these is 10. So 10, 20, and this would be 30, 30, and that would represent 30 miles per hour. And to that shaded region, we're going to add this rectangle right here. So this rectangle would be the base, right, which would be 3 hours still, times the height, which is 10, 20, it'd be 30 miles per hour also. Okay, so this becomes 45 miles. Plus, and then 3 times 30 would be 90. So this would be 90 miles. So from this, we could tell that the distance that the car traveled would be 135 miles. So that would be how far it traveled, because that is the area, and the area represents, even from this question up here, the area represents the distance traveled, okay? So the area under a curve, between the curve, now in this case, it's not a curve, it's a straight line, right? But we can call that a curve. Between the curve and the x-axis, that area gives us, for a velocity time graph, it gives us the distance traveled, okay? So another method to do the same problem, and we'll still get 135 miles, and method 2 would be a trapezoid. And I'm teaching you this because we are going to need this towards the end of this unit, okay? So the area of a trapezoid is 1/2 times the height times the bases, and we say the sum of the bases, which is base 1 plus base 2. Now, how do you know which one are the bases? The bases are the two sides that are parallel. So in this case, these two right here would be the bases because they're parallel. The height is always going to be perpendicular to the bases, so that would be this length right here. Okay, so in this case, the distance would equal 1/2 times the height. The height is perpendicular to these two bases, so it'd be this, 3 hours, times, and then the sum of the bases. So this base right here is 30 miles per hour, plus, and then this base is 60 miles per hour. And if we add those, we get distance is equal to 1/2 times 3 hours times, and 30 and 60 makes 90 miles per hour. And it's actually easier to take half of 90 than half of 3. So I'm going to do half of 90 is 45. So this would be 3 hours times 45 miles per hour. And so our hours are going to cancel here, and 3 times 45, and that would also give you 135 miles. So the big idea here is that we can get the distance traveled by finding the area between the curve and the x-axis, okay? For this next problem, okay, a particle starts at x equals 0 and moves along the x-axis, and here's the velocity for time t is greater than or equals 0. Where is the particle at t equals 3? So it's starting here. So basically, we've got to find how far did it travel in this time of 3 hours, okay? So since this is not a straight line, it's a curve, all right? What we're going to have to do is we're going to have to estimate it, because we can't make nice geometric shapes like we did the last problem, like a triangle and a rectangle, okay? But we can estimate it, and we're going to use what's called LRAM, and LRAM stands for Left Rectangular Approximation Method. So LRAM. And what that stands for is Left Rectangular Approximation Method. Okay, and then what we're going to do, it's called three partitions. So we want to know from 0 to 3, and so we're going to calculate what is our change in x, and we want to do this with three rectangles. Okay, so my delta x, okay, is going to be 3 minus 0, and why 3 minus 0? Because we're starting at 0 and we're going to end it at 3, so that distance is 3. So 3 minus 0, and we're going to divide by how many partitions there are. So this is 3 partitions. And so that gives you 3 over 3 equals 1. Now, you may not understand that completely yet. We are going to do more problems that involve this, okay? So that means we're going to make 3 rectangles, and each one is going to have a width of 1. So we're going to go from 0 to 1. We're going to go from 1 to 2 and 2 to 3. So we're going to go from 0 to 1. And basically what we're going to do is, because it's the LRAM, all right, LRAM stands for the left. So what we're going to do is we're going to come up, all right, and we're going to build this rectangle, and we're going to go up until the left side, which is where my finger is, right, until the left side hits the curve. The left side, that's why it's called an LRAM. So we're going to stop it right here at this point right here. So we are going to stop right here, and we're going to build a rectangle, okay? So here's my first rectangle. All right, and then we're going to go, so that was the first one, right? And we want to do 3 of these. So 0 to 1, and then we want to go from 1 to 2. And again, we're going to go up until the left side of this hits the curve. So that would be right here. And so that would be the top of our rectangle. Okay, so that's from 1 to 2. And then we're going to do another one from 2 to 3. So from 2 to 3, and we're going to go up until the left side hits the rectangle. And that would be right here. So right here, and then we're going to extend this from here to here. Okay, so I'm going to pause it, and I'm going to shade these 3 rectangles in. Okay, so to estimate the distance, so this time I'm going to use D, and I'm going to use approximate, okay? The area of this rectangle would be 1, so that represents 1 hour. So 1 times, and the height of it we would get by finding V sub O, or not V sub O, V of 0, I should say, V of 0. So that's this one right here, okay? And so we're gonna get the height of this rectangle by finding the velocity at time 0, and then adding that, and then the next one would be 1 hour, and then times, and this one we'd have the velocity at 1. That's how we'd get the height of this rectangle, is by finding V of 1. And then plus, and then this one right here, it would be 1 hour again from 2 to 3. And then it would be V of 2 to get that height of that rectangle. Okay, so this would be 1 hour times, and then V of 0 would come out to be 5. Okay, so 5 miles per hour. And then plus 1 times, and V of 1, we can just read it off the graph here. That would be 7. You're not always going to be able to read it off the graph, okay? And then plus 1 times V of 2, and V of 2 is also 7. So an estimate for the distance traveled during this time is 5 plus 7 plus 7, and this would be 14 plus 5. So that would be the distance, and the approximation for the distance would be 19 miles. Now, why does this kind of work? Okay, it kind of works because this one was under, right? And so this part, and then this one was over, and this one's a little bit under, but pretty close, right? This part right here could fill in this, and we would be kind of close to having a good approximation for this. Okay, so how can we get an even better approximation? Make more rectangles. And that is going to be a big deal. Like, we're going to make more and more rectangles. And I should have said this is V of t right here, this curve. All right. So the next one we're going to do is we're going to do the same thing, but we're going to do 6 rectangles. Okay. So for this one right here, okay, we're still going from 0 to 3, but I want to do 6 of them. So my delta x, my width of my rectangles is going to be still 3 minus 0 because I'm starting at 0 and I'm going to end it at 3. So that'd be 3 minus 0. These are the end points, right? The start, okay, or this is the end and this is the start over, but this time I want to break it up into 6 of them. So this is the number of partitions right here. So that means 3 minus 0 is 3 over 6. 3 over 6 is 1/2 or 0.5. So this time I'm going to make 6 rectangles, but the width is going to be 0.5. So as I make more rectangles between 0 and 3, the widths are going to get smaller and smaller and smaller. Okay. All right. So for this one, and it's still LRAM. So we're going to go from the first one is going to be starting at 0, going to 0.5, and we're going to go up until the left side of our rectangle hits the curve. So that would be right here at 5 again, right? Now we're going to come up with a formula that generates these. And so what we're going to need to know is we're going to need to understand over a period of time, right? We're going to need to understand how this LRAM works, okay? And so that's the first rectangle. We're going to have 6 of them. So the next one's going to go from 0.5 to 1. And so we're going to go up. And here's an example if you can't read it off the graph, right? The left end is going to, the left side of this rectangle is going to stop right here. So this would be the height of the next rectangle. Okay, so this height right here is V of 0. And this height right here would be V of 0.5. And then we're going to go from 1 to 1.5. And we're going to go up until the left side hits the curve. That would happen right here. And then we're going to go across. And then down. And that's our next rectangle. Okay, so we have 3 of them. We're going to do 6. The next one's going to go from 1.5 to 2, and we're going to go until the one at 1.5 hits the curve. That would be right here. And then this is going to be a little bit over. So this would be the point right here. So we're always on the left side of the rectangle. Okay, that's why it's LRAM. And then 2 to 2.5, and we're going to draw it until the left side hits the curve. That would be this point right here. We're going to go across and down. And then from 2.5 to 3, and that'll be our 6th one. And we're going to stop it right here and then go across and down. And so that'd be the point right here. And notice all of these, this would be V of 0, V of 0.5, V of 1, V of 1.5, V of 2, and then V of 2.5. We don't use V of 3. We don't use V of 3, right? Because we're not basing the height off the 3. It's the left side of this, which is 2.5, right? Okay. I'm setting you up for something by saying all that, okay? All right. So I'm going to pause and I'm going to shade this in. You don't need to see me color, okay? Okay, so let's do the math involved in getting this, okay? So the distance we would estimate, and this would be a better estimate. This is going to be a better estimate than this one because we're using more rectangles. And I point to this one because that's the 3 partition one, okay? This one's going to be a better estimate, all right? So the width of this rectangle is going to be 0.5 times V of 0, and then plus 0.5 times V of 0.5 plus, and then 0.5 times V of 1, and then plus 0.5 V of 1.5, and then plus 0.5 V of 2, and these are going to go up by 0.5 each time until we're not going to go all the way to 3 though, right? We're going to stop it at 2.5. So, and then plus 0.5 V of 2.5, and that's my 6 rectangles, right? Okay, so that means the distance can be approximated by 0.5, and v of 0 is 5, and then plus, and then 0.5. V of 0.5, okay, so we can't read it off the graph, but if we put it into the original function that's way up here, right? I'm going to tell you that turns out to be 6.25. And then plus 0.5, and then v of 1, and v of 1 turns out to be 7. And then plus 0.5, and v of 1.5, v of 1.5 is 7.25. And then plus 0.5, and then v of 2, and v of 2 is 7. And then 0.5 times v of 2.5, and v of 2.5, we can't read it off the graph, but if we put it into the velocity function from above, it turns out to be 6.25. And we put these in our calculator, okay, and we get a distance, 0.5 times 5 plus 0.5 times 6.25. We just put all those into our calculator, and we wind up with 19.375 miles. Okay, so that's a better estimate, right? Okay, and so the idea here is, okay, so what would be even better if we did 12 partitions, or if we did 24 partitions, or where we're going with this, infinite partitions. So we're going to make the partitions go to infinity, which means every time we divide, right, by a bigger and bigger number, this is going to get smaller and smaller and smaller until at some point the two sides collapse, and you no longer actually have a rectangle, you have a line segment, and these are drawn by infinite line segments. Okay, that's coming. That's coming. All right, not yet. All right, so really you just got to realize, okay, I can find the distance traveled by taking the area under the curve. Okay, and when it's not a nice geometric shape like this, you can't get a nice geometric shape out of something that's curving like this, then you're going to have to approximate with rectangles like we did. Okay. All right, so same problem, but we're going to this time do RRAM, and I meant to write this. We're going to do 3 partitions. And we're still going to go from 0 to 3. Okay, so that means our delta x is going to be our endpoint, which is 3, minus our starting point, which is 0. So 3 minus 0, and divide by how many partitions there are, in this case 3. So that'd be 3 minus 0, which is 3 over 3. So my delta x is going to be 1. So my rectangles are going to go up. And the first rectangle I'm going to draw is from 0 to 1, and then from 1 to 2, and then from 2 to 3. Now, this is RRAM, right? So that stands for right rectangular approximation method, okay? And so what we're going to do with RRAM, LRAM was we use the left side of the rectangle, right, to find the height of the rectangle. This time we're going to use the right side of the rectangle. So this time we're going to go up until the right side, which is my pin, right, until it hits the curve, which in this case would be right here. Okay, so that would be my first rectangle. Because my width is going to be 1 here, and my height is going to be determined by going up until the right side hits it. So that would be v of 1, right? And then we're going to make our next rectangle from 1 to 2, and we're going to go up until the right side hits it. So the right side is going to hit it right here. So that's going to be v of 2. And then we're going to end this by going from 2 to 3 and going up until the right side hits it. That'd be right here in this case. All right, and I'm going to pause it, and I'm going to shade these in. All right, so I've shaded them in. Okay, so this time to get an approximation for our distance, okay, because our partitions are, the width is going to be 1 each time, right? We're going to go from 0 to 1, right? So that'd be 1 times V of, now we're not going to start with the starting point, right? We're not going to start at 0 because we want to use the right one. So we're going to start one away from the start, which would be at 1. So this would be V of 1, and then plus 1 for this width, and then it'd be 1 away from this one. So V of 2, and then plus, and then from 2 to 3, and it'd be V of 3. So this time on the right one, we're going to include the end point over here, right? We're going to include the one at 3. So this distance could be approximated. This would be 1 times, and V of 1 is 7, plus 1 times, and then V of 2 is also 7, and then plus 1, and then V of 3 is 5. So this turns out to be 7 plus 5, or 19 miles. Okay, so once again, I want to say this, okay? This LRAM and RRAM turned out to be the same number. They don't always. It's just the way it has to do with the symmetry of this, okay? And where we started it and ended it, okay? But please don't think LRAM and RRAM are always going to equal the same number. They won't, okay? So RRAM is, we use the right side. So we're always going to be, whatever this delta X is, that's where we're going to put the first value into our function from the start. So we started at 0, 1 away would be 1. So that's why we have V of 1 here and not V of 0. Okay. And the last one we're going to do is MRAM. And MRAM stands for midpoint rectangular approximation method. I almost forgot there. What does the M stand for? It's midpoint. Okay. So we're still going to go from 0 to 3, and we still want to do 3 partitions. And I'm just doing 3 so we can get through this fairly fast, okay? And so 3 partitions, we're going to go from 0 to 3 still, okay? So my delta X is going to be 3 minus 0 divided by how many partitions, which in this case is 3. So that'd be 3 over 3, which is 1. So this time, okay, I'm not doing the left, I'm not doing the right, I'm doing the middle. So we're going to go from 0 to 1 because I'm starting at 0 and I'm going to go 1 away, right? That's going to be my width of my rectangle. And I'm going to go up when the middle of this rectangle, so like 0.5, when it hits the function. So that's what an MRAM is, okay? So it's in between, it's the value in between 0 and 1. So right here, and then I'm going to go straight across. And so this would be my first rectangle. And what tends to happen is part of it's over and part of it's under. And so kind of the thought is that this part that's over kind of matches with this part that's under, okay? So then we're going to go from 1 to 2, right? 1 to 2, and we're going to use the midpoint, which is 1.5, to determine the height of it. So we're going to go all the way up until right here. Hopefully you're catching on to how this LRAM and RRAM, what it all means. So that's the next one. And then we're going to go from 2 to 3, because we're ending on all of these at 3, okay? And so from 2 to 3, and we're going to use the midpoint, which is 2.5, to determine the height of this rectangle. And so it's going to stop right here. And that'd be the height of my rectangle. And then I'm going to come straight down. Okay, so I have 3 rectangles. That's the 3 partitions. And I'm going to pause it once again. All right, so this time to find the distance, okay, each width is going to be 1. And V of, and again, from 0 to 1, the midpoint is 0.5. So we're going to find V of 0.5. And then plus 1, because this width is 1 hour, right? That represents 1 hour. And then going up, this would be V of 1.5. And then plus, and then 1 times V of, And for this one, we're going from 2 to 3. So the midpoint would be 2.5. So that'd be V of 2.5. And so for this one, the distance would be 1 times, and V of 0.5 is 6.25 plus, and then 1 times V of 1.5, and V of 1.5 is 7.25 plus, and then 1 times, and then V of 2.5 is 6.25 again. And so that means if we put these in our calculator, it'd be 6.25 plus 7.25 plus 6.25, which gives us a distance of 19.75 miles. All right, so LRAM is we use the left side of the rectangle to determine the height. RRAM, we use the right side to determine the height. MRAM, we use the midpoint of the width of the rectangle to determine the height. Okay, and however many partitions, if this was let's say this was 8 partitions, okay, let's say we did 8 partitions, then, and I want to go from 0 to 3, so this would be 3 minus 0, and then I would need to divide by 8, so each one would be 3/8. Okay, that would be hard to do, right? That's why we didn't do 8. Okay, let's do an actual problem now to help you illustrate this without a graph. Okay. So for this problem, we have a rocket that has positive velocity after being launched upward with an initial height of 0 feet at time t equals 0. And so these are the different velocities, okay? And we want to find the approximate distance traveled by the rocket in 80 seconds. So that'd be from 0 to 80, and use RRAM with 4 intervals of equal length. So 4 intervals of equal length are my partitions. So this means 4 partitions. Okay, so I need to calculate my delta x. So my delta x is, we want to do the 80 seconds, right? So we're going to start at 0, and we're going to end it at 80. So that'd be 80 minus 0. And then we want to divide by 4 partitions. So that'd be 80 divided by 4, which means 20. So my rectangles are going to have a width of 20, okay? So we're going to go from 0 to 20, and then 20 to 40, and then 40 to 60, and then finally 60 to 80, okay? So we're going to do, and the other thing to pay attention to is RRAM, okay? So that means my distance is going to be approximated by a width of 20, that'd be 20 seconds, right? And this would be the first interval from 0 to 20, right? And we're going to multiply that by V of, since we're doing RRAM, we're going to do V of 20, the right side. So this is the left side of the rectangle. This would be the right side. So V of 20 plus, and then 20 times V of, and the next rectangle we're starting at 20 and ending it at 40. So that would be V of 40 plus 20 times V of, and the next rectangle we're going to go from 40 to 60. So that'd be V of 60. And then the fourth rectangle is going from 60 to 80. So that'd be plus 20 V of, and we're doing RRAM, so it'd be V of 80, because we're doing the RRAM, which is we're going to use this one, the 20, the 40, the 60, and the 80, because those are all the right sides of my rectangles, okay? So this turns out to be, the distance is 20 times, and then V of 20 is 22. And then plus 20 times V of 40, which is 35. And then plus 20 times V of 60, which is 44. And then plus 20 times V of 80, and that'd be 49. And we put those in our calculator, and I've already done it. So that, and I already know that if you put those in your calculator, you get 3,000. And the units on this would be, since this 22 is feet per second, and this is seconds, this would just be 3,000 feet. Okay, so that's an estimate, an approximation of how far the rocket traveled. Okay, next one we're going to do is LRAM, okay, from a table. And by the way, this is always asked every year. It's asked on the AP exam, is to do something similar to this, okay? So we want to do LRAM, Okay, so with 4 intervals of equal length, so I don't need to recalculate my delta x because it's still going to be 20. So my distance can be approximated by 20 times v of, and now since we're doing LRAM, it's going to be the left side. So this would be v of 0 plus 20 times v of, and so the next rectangle is going to be between 20 and 40, and to find the height of it, we're going to use v of 20 plus 20 times v of, and the next rectangle goes from 40 to 60, and we're using LRAM, so we're going to use v of 40. Also, since the delta x is 20, we're starting at 0. This is always going to go up by my delta x. So next we're going to be v of 60. So plus 20 v of 60, and that's the one between 60 and 80, and we use v of 60 because we're using the left side of it to determine the height. So then the distance would be 20 times 5, because v of 0 is 5, and then plus 20 times v of 20, and v of 20 is 22. And then plus v 20 times v of 40, and v of 40 is 35. And then plus 20 times v of 60, and v of 60 is 44. Okay, and once again, I've already put this one in my calculator, so we're not going to have to worry about that. This turns out to be 2,120, and once again, this would be feet. So using RRAM, see the RRAM and the LRAM don't necessarily come out to be the same, right? The RRAM turned out to be 3,000 feet, and the LRAM turned out to be 2,120 feet. Okay. And so we're going to do this one more time, but next one is MRAM with 4 subintervals of equal length. Okay. So the next one is we're going to go from 0 to 20, but we're going to determine the height by the middle one. So that would be v of 10. Okay. So for this one, the distance is going to be 20 times v of 10, and then plus 20. And this number right here is still going to go up by 20 because we're going to add 20, and that would be 30, right? V of 30. And I should have I didn't mean to put a parenthesis there. So it'd be 20 times v of 30. So 20 times v of 30, and then plus, let me zoom in a little bit. I know you can't see the table anymore, okay? But you have it on your paper too. Okay, so plus, and then 20 times v of, and the next one, I'll slide it down. Okay, so the next one's between 40 and 60, so the middle is 50. So v of 50. And then plus, and then 20 times v of, and we're going between 60 and 80, and so it's 70. So notice on all of these, right, once you get the first one going, you can just increase it by your delta x, right? And our delta x in this case was 20, right? And then 20, and then 20, right? So distance on this one is 20 times v of 10 is 14, plus 20 times, and v of 30 is 29. And then 20 times v of 50, which is 40. And then plus 20 times v of 70, and v of 70 is 47. And I read those all off the table. And then putting that into our calculator, right? I wouldn't expect anybody to do that in their head. All right, this turns out to be 2,600 feet. So we did RRAM and we got a value. We did LRAM, we got a value, and we did MRAM and we got a value. And they're all different, right? But they're all 3 approximations. It's just the method you use to approximate this height. Okay. And that's what I want you to understand today is that if I figure out the area under a velocity time curve, okay, if I can figure out the area, then I'm going to get the distance traveled by an object. Okay. And so if right now we're going to use calculus to actually get the exact, so right now we're approximating, right? But we're actually going to be able to find the exact value of the area under a curve. So in using calculus, because it has to do with limits and shrinking the rectangles and making more and more rectangles, right? And infinite mini rectangles. All right, you guys, that's it for today. Hopefully you enjoyed this, and I will see you. Bye.